Today, we're going to talk about quantum computing applications in chemistry. For many years, computational chemists have been using classical computational methods to attempt to solve chemistry problems. My background is in software development, but I'm particularly passionate about the applications of software within chemistry and the particular advantages that quantum computing has the potential to bring. Many computational chemists will use popular software packages such as Gaussian, PySCF, and Psi4. These, plus many others. All of these different packages provide a suite of tools to enable computational chemists to do research into various different types of chemistry problems. And they all use particular sets of data to be able to do this work. And some of the important data points can include information about a molecule's ground state energy, excited state energy, as well as potential energy surfaces, and many more. But how do we actually calculate this information for a given molecule? Let's take H2O, for example. So in order to calculate the ground state energy of water from a classical perspective, first we're going to need some information about the molecule itself. We want to know the atoms that are involved, as well as maybe some different coordinates in space. And as well as this, we're also going to take a set of functions known as a basis set, which you can think of as essentially a mathematical representation of the different orbitals within the H2O molecule. So in order to, and then we take this information, and what we're going to do is we're going to plug it into a Schrödinger equation. Schrödinger equation is a very important equation within chemistry and quantum mechanics generally, and it defines the quantum system itself. And this value E here represents the energy of our quantum system. In this case, our quantum system is the H2O molecule. So if we minimize this value of E, we can get the ground state energy. So how do we actually go about finding this minimum value of E? Well, there are a few different things we can do, but firstly what we're wanting to do is make some assumptions to simplify the problem a bit. We can use the Born-Oppenheimer approximation, as well as the Hartee-Fock approximation. And these assumptions essentially make it easier to compute solutions to this equation. And once we've done that, our output will be an approximation of that ground state energy. So far, everything we've done up till this point, we can do classically with classical computers. However, there are a few problems with this. The first one being that the accuracy of this value will decrease as the complexity of our quantum system increases. As well as this, if we want to do any further processing beyond Hartee-Fock, this becomes exponentially more difficult and computationally very expensive very quickly. And this is why software packages like the ones I mentioned before will often leverage GPUs and high-performance computers in order to try to solve this equation for more complex molecules. But quantum computers have the potential to simulate these more complex molecules more efficiently and to a higher degree of accuracy than just Hartee-Fock processing. And this is because quantum computers process information in a fundamentally different way than classical computers do. So let's go back to our Schrödinger equation for a minute. We can essentially map this equation onto qubits, onto quantum bits. And we can also incorporate some of these approximations as well. So we can represent this in quantum circuit form. And because we've done this, now we can leverage key quantum phenomena such as superposition and entanglement. Then, if we're using Qiskit Runtime, we can take this quantum circuit and use it together with an estimator primitive, as well as an optimizer. And we can take all of that and plug it into a variational quantum eigensolver algorithm. This is a very important quantum computing algorithm that enables us to calculate eigenvalues efficiently. So if we're using primitives, these are unique to IBM's Qiskit Runtime. They are predefined programs that help users to optimize their workloads and execute them efficiently on quantum systems. The estimator primitive in particular makes it easier to extract solutions from this circuit, and also gives us incredibly fine-grained control over the system hardware and optimization routines so we can generate the best results possible. So once we've done all of that, we will get an output, which is, again, an approximation of the ground state energy for our H2O molecule. But this value that we've calculated here is often more precise than just doing Hartee-Fock calculations alone, and it doesn't consume compute resources as fast. And this is why quantum computing researchers, particularly in the field of chemistry, are incredibly excited about the potential for quantum computers to have a real impact on the chemistry industry specifically. And with open source tools like Qiskit Runtime and Qiskit Nature, anyone can get started experimenting with this today. And we'll leave some links in the description for you to get going with that. Thank you very much. I hope you enjoyed this video. Remember to like, subscribe, leave any questions that you have in the comments, and remember to check out our other quantum videos on this channel.